As we begin our next unit, we'll be looking at the periodic table, and we will be looking at the information that we can obtain about an element based upon its location on the periodic table. Now, when the periodic table was laid out and designed, they did not know anything about the electronic structure. They only knew about their chemical and physical behavior, and so they lined things up in similar ways according to their similar behavior. And now, as we understand the electronic structure, we see that these electrons and where they are located in the periodic table that give us information about the way these elements will behave chemically as well as physically. So let us begin with our first learning objective. In our first learning objective, we're going to be looking at the connection between the electron configuration of an atom and where it is located on the periodic table. Now, we have learned to use a periodic table to come up with the electron configuration, but we really haven't looked at the similarities of elements within a group, within a family. Let's look at a particular family. We're going to start by looking at the halogens. So we're going to do the electron configuration of each of the halogens. Let's begin with fluorine. So we look at fluorine. What I want you to do is maybe pause the video, pull out a periodic table, and try to do the electron configuration of each of these as we go through it. So you find the noble gas before fluorine and work your way over to it. And you come up with helium 2s2 2p5. Then we'll do it for chlorine. Okay, that'll be next halogen. Well, if we do its electron configuration, the noble gas that comes before it is neon, so it's neon 3s2 3p5. And then we can do it for bromine, and if we do it for bromine, the noble gas that comes before bromine is argon, and we work our way over to the bromine, and we have argon 4s2 3d10 4p5. So as we look down that family there, we're going to see what they have in common. And that is, if you look at the highest principal quantum number, N, for these, there's your N, okay? And you see how many electrons are in that with the highest N. You see that there are 7 electrons located there. And here we have an N that is 3, and if we look at all of those, we have 7 electrons. And if we look at bromine, while there is this D submerged in the middle between those S's and P's, if we look at the highest N, okay, here we have again 2 plus 5, we have 7 electrons in that value, that highest N value. So we see that all of these have something very much in common for the halogens. If we look at a periodic table and we find those halogens, we will see a number associated above this family here that's the same as the number of electrons we saw in that. So all of those will have that in common. They will have 7 electrons in that shell that contains the highest N. And this is going to be true for any one of these groups here. Now, it only works for our representative elements. We cannot do this for any of the transition elements, okay? But it does work for those representative elements very, very nicely. So as we notice the similarity in the families, okay? Electron configuration causes these families to have the similar behavior, chemically and physically. So within a group, because they have a similar electron configuration, they're going to behave similarly. So electrons that are written after that noble gas core are called the valence electrons, or the outer electrons. For a family, or for that group as we go down, they will all have the same number of these valence electrons. And it's these valence electrons that are the ones that are involved in chemical bonding. So when we start looking at the atoms combining into forming compounds, we'll be utilizing those valence electrons. And as we saw on the previous periodic table, the group number for those representative elements is equal to the number of valence electrons. So that is an important piece of information to keep in mind. You must keep in mind that it's for the representative elements and not for the transition elements. All right, so we're going to learn some group names here, but just let me re-emphasize, okay? The group number right here is the number of valence electrons in those representative elements. So if we wanted to know how many valence electrons 10 has, we would find 10 on the periodic table, which is located right here, and we would go up to this number that has the A associated with it, and we would know that 10 has 4 valence electrons. So we're gaining information about the periodic table from about the elements from where they're located on the periodic table. So our periodic table is a wonderful cheat sheet for us. We'll always have access to it, or you always have access to it when you take your exams. Okay, so there's some groups that we need to know the names of, because I will use these names as we proceed through this unit and for the rest of our chemistry course. The first one we want to make sure we know the name of is our alkali metals. The alkali metals are this group right here, the 1A family. So sometimes you could just call them the 1A family, but they're the alkali metals. The next is the alkaline earth metals. The alkaline earth metals are the 2A group. Okay, so those are the alkaline earth metals. Alkaline means basic. Okay, if something is alkaline, and when we're talking about acids versus bases, they are basic in their properties, and that's where they got their name. The next we have is the noble gases. The noble gases are located right here, that last group of representative elements. We see that it has a 8 above them, so I have 8 valence electrons, and that is true for every element except for helium. Helium couldn't possibly have 8 valence electrons because it only has 2 electrons in its entirety. So helium has 2 valence electrons, but every other element in that group has 8 valence electrons. Next we have the halogens. The halogens are these here. Now I used that term at the very beginning of our slide as we went through fluorine, chlorine, bromine and did their electron configuration, but those are our halogens. Another thing that we need to make sure we know about periodic table is that we can locate things by the period they're located in. So as we go across, those are periods. So that's the first period, this is the second period, this is the third period. So if I were to ask you for a halogen in the 4th period, you would be able to locate bromine as a halogen in the 4th period. Valence electrons are in the shell of that's equal to that number. So when we did the electron configuration of bromine, we'll write it down here again, is argon, okay, 4s2, 3d10, 4p5, okay? We see that the number 4 is associated with that period number. Okay, so use your periodic table and use what you learned without having to do the whole electron configuration. Tell me how many valence electrons are in calcium. If you said 2, then you are correct. If you didn't say 2, let's locate calcium. There it is. There's the group number. And so we have 2 valence electrons, and it works because it's a representative element and not a transition element. Now let's refresh our memories on various locations of areas on the periodic table. I've been using the term representative element, and maybe you're not familiar with what that means. Everything that is shaded in this similar color here are our representative elements, and depending on what screen I have, it's kind of different colors. But representative elements are these elements here. Okay? The definition of representative elements comes from their electron configuration. So they have incompletely filled S and P sublevels. Okay? So when we're dealing with the representative elements, their S and P subshells are incompletely filled to be in that category. So if you looked at the electron configuration, stopped and did it for any one of those, you would know you were dealing with a representative element. Now we've already talked about the noble gases, and we know what they are, but how are they defined in terms of their electron configuration? Well, the noble gases have completely filled S and P, okay? So the S has 2 valence electrons, and the P will have 6 valence electrons for all of the noble gases. So they stand alone as a unique feature of our periodic table because of their completely filled S and P subshells. So the representative elements have incompletely filled S and P, but the noble gases have completely filled S and P subshells. The next one are our transition elements. Now our transition elements are these, and sometimes they're called transition metals instead of transition elements, so we could change the name there. Because they're all metals, that would be okay. What is unique about them? So in terms of electron configuration, what transition metals have is a D that's incompletely filled. So it's got electrons in the D subshell, anywhere from 1 to 9, and that gives them unique properties, and so they categorize them all together as transition metals. Now the lanthanides are down here in the bottom. Remember, we take them out of the periodic table. They are located between here and here in the periodic table, named after the element that comes before it. Sometimes you will see it written down there with the series, but there's the lanthanide series and the actinide series. And what's unique about the lanthanide series is that they will have electrons going into the F subshell, and it will be the 4F subshell. The actinides will have them going into the 5F subshell. And then we've got one little group of a few elements here. They don't have a name. We'll just call them the zinc, mercury, and cadmium group right here. What is unique about them? Well, they all will have a 10 valence electrons. So they won't be considered transition elements because the fact that their D subshell is completely filled up gives them unique properties. Okay? So the way the periodic table is laid out and the way these elements are grouped together all come about based upon their electron configuration. And we group them this way because we can study them as a group and know something about every element in that group by studying the group itself. That's a lot of what chemistry is about. Chemistry is very, very often about taking things and putting them into categories. And from that category, knowing things about the category, therefore you know something about every piece of matter that fits into that category. When we group things together, we know things about that element or about that specific piece of matter. And here we're just grouping things according to their location on the periodic table, according to their electron configuration. So this completes learning objective number 1, where we are examining the electron configuration and how the periodic table and the electron configuration kind of go hand in hand.